I'm here to interview Diego, who's one of the founders of Cartesi and one of the brilliant minds behind the Cartesi Machine and a couple of other components in the Cartesi system. And basically, we wanted to sit down because, well, from my point of view, I had a bit of curiosity about like how did this thing came about. How does some of these technical things actually work? I have been reading a lot of the documentation and so on, and articles and kind of like all the Cartesi stuff out there. But because I wasn't, let's say, a part of the project from the beginning, there's a lot of things I don't know. So I thought to basically to go to the source of somebody who probably remembers everything about how things went down. So Diego, could you just quickly just like say something about yourself, like where what you've been doing, kind of like what's your background?
Yeah, so I'm originally a researcher, an academic, and I did a PhD in Princeton in computer graphics. Then I worked at Microsoft Research for a bit as a postdoc, and then I came back to the Mathematics Institute in Rio to become a professor there, and focusing mostly on computer graphics, image processing, parallel algorithms, high performance computing, stuff like that. And that was about until 2018. It was the only thing that I did was research and publish papers and advise students and teach. And then I became aware of interesting problems in the blockchain space and became interested in that, right? So that's more or less my background.
Cool. So maybe let's start off with that. Let's say the story. Like how did the Cartesi machine actually get invented?
So Augusto, who has a similar background, though more in theory, he's a probability professor at IMPA. And we became friends there because we became professors more or less around the same time. And so he came around and he, because he knows I'm more of a computer scientist, he said, I'm working on this interesting problem that a friend of mine gave me. I want to do something like Kaggle, but I want to do it on the blockchain, and it's difficult to write a program that will verify if some machine learning problem was solved correctly. Like we really can't do this on the blockchain. It doesn't scale enough for this. And so I want to like come up with a VM or a way to run programs outside of the blockchain in a way that can be verified on chain, right? And this was more or less the same time that TrueBit was appearing, maybe a little bit before they came public with their idea of how to do a similar thing. But I really liked the idea of what we call the verification game. This turns out Augusto independently came up with this idea, but it had been published a lot earlier. Later we found out by Canetti and even before that in a different variation. And I really liked that idea, to be honest. I thought this is really cool because we can run a computation that performs n steps outside of the blockchain, and then the blockchain only needs to spend a logarithmic amount of steps to figure out who is cheating. I thought this was really cool. But because I'm an engineer, I thought that, well, this obviously the way this has been done so far, it will only ever be used for toys, because there's an entire ecosystem of software that has been created to support modern development strategies, right? Every programmer out there actually relies on the work of, I don't know, like billions of hours of development from other developers, right? And these things all interact and they rely on each other, and there's an operating system underneath that is what enables these things to interact with each other, right? So I felt, okay, we need to run these computations inside an operating system, otherwise people will be kind of tied, their hands tied, will have their hands tied, right? And And so we need to come up with an emulator that emulates an architecture that actually supports an operating system, so that people can have a better experience programming for it, right? So that's how the Cartesi machine came about. It's basically an emulator for a real quote unquote architecture that you can boot an operating system and run the software on it. And then what architecture is that, right? So since we are in the business of getting people to reuse all that was already there, it wouldn't make any sense for us to come up with something on our own. We are also not arrogant enough to think that we can do everything better than what already exists. And it turns out that about that time, RISC-V was gaining traction, right? So RISC-V is an open and free standard. It was created by professionals that only do this. That's their life, right? This is what they do, is to create this architecture. And it has the support of a bunch of big corporations, Google, NVIDIA, Qualcomm, people that know this stuff. They know what they're doing, right? And it has already a lot of software written for it. And in fact, you can boot Linux on it. And there's a compiler many compilers that target it. And so all this software environment that we wanted to enable people to use would be available if we supported RISC-V, right? So that's what we did. We created an emulator based on the RISC-V architecture to do that. And yeah, so that's the story, how it came about.
Mm-hmm. So one of the things that is like one of the properties of, let's say, the Cartesi machine is this whole, it's reproducible, deterministic, and so on. Why is this actually important?
Yeah, because the way consensus work in the blockchain, it depends depending on the particular base layer that you're talking about, but it's more or less works like this, right? So you submit a transaction to some pool, and then the miners pick these transactions, and they put them in a block, and they execute them, and these things produce certain side effects that are taken into account and locked into this ongoing state of the blockchain, and then other transactions are sent to this pool. Some other miner picks, put in a block, and refers to the parent block. But he will only point back to this particular previous block if he agrees with the state changes that happen, right? And so it's really important in decentralized computation that people are able to agree on results of computations, right? And it turns out that if I run a program in my computer and you write a program in your computer, there's really no way for us to fight over disagreements, or even worse, even if we both are honest, it's very likely if we didn't write our program very carefully, it's very likely that we'll produce different results. And this could happen for a variety of reasons. The program might check the time of the day, for instance. This would be the dumbest thing that you can do, right? If I run not exactly at the same time, they won't match. Or it could check the mouse, something that input, like some user input or a keyboard input or a network connection or maybe the state of the file system. They're very subtle things that could cause two honest executions of the same program to actually produce different results, right? So we can't have any of that. And so in our emulator, the first thing that we need to guarantee is that it is self-contained. The executions are self-contained, right? So you define the initial state of a machine in a way that is fully self-contained, and you run it, and while the machine is running, there's nothing that is interfering with it from the outside. So the sequence of states that the machine reaches is perfectly defined by the initial state of the machine. There's no external influence on it, right? So this is a property of the emulator. The other thing that we need to make sure is that it is reproducible, right? So self-contained means there's no external influence, and reproducibility, some people call this determinism, but determinism has a computer theory meaning that has nothing to do with this. It's related to whether you do a bunch of things in parallel and then, or if you do things sequentially, more or less. And so we prefer reproducibility. So this means that it doesn't matter who is running this program. You run it, I run it. It doesn't matter the computer I use to run it. It doesn't matter the operating system under which I'm running it. It doesn't matter how many times I run it. It always produces the same sequence of states. And surprisingly, this is not true necessarily unless you're careful when you write your software. And the final property that is also not common in emulators and in virtual machines is that we can stop our emulator after every instruction. And in fact, later on, we might talk about micro instructions. We can stop it at any time, say, save it to disk in a way that you can pick up the computation later. And you will continue exactly as if you didn't stop it, if you kept going. And more than that, the entire state on which the future of evolution of this computation depends, it is accessible from the emulator, right? There's nothing hidden. There's nothing hidden in somewhere that you might forget to take into account, and that might change the result of the computation. Everything is transparent, and it is transparent in a way that facilitates this verification game type dispute resolution that we also might get into in later on. And so it is possible to ask from the emulator, okay, give me a hash that completely describes this state, and also and this hash we'll say this is a Merkle hash, so it has some pretty cool properties that allow me, if I know the state hash, then I can give you a proof concerning the value of any piece of the state, and this can be checked. If we agree on the state of the machine, then there's no way we can disagree on the value of any word on the state as well. So these three properties, determinism, or reproducibility, as we prefer to call it, self-containment, and transparency, are things that are not very common in other emulators, or in any emulator, to be honest. And our emulator has those properties.
All right. So not sure if there's other kind of like projects out there kind of using RISC-V as well, like other kind of virtual machines and so on. Like what makes like Cartesi machine really special in your opinion?
Yeah. So here we have to get into a bit about what is the RISC-V instruction set architecture, and it's actually divided into two parts. And one of them is the privileged architectures. That is the part of the architecture with which people writing operating systems are concerned. And the other is, by comparison, called the non-privileged, or the user space part of the specification. And that is what normal people would care about, right? And even this is also separated into a bunch of different extensions. So you can say that you support RISC-V if you support a tiny bit of the non-privileged architecture. So why is this distinction relevant? So first is, we have to talk a little bit about how programming languages work, I guess. And so the C and C++ standards make this distinction pretty clearly. They talk about two types of implementations. One implementation is called a freestanding implementation, and the other is called a hosted implementation. And a freestanding implementation is the bare minimum that you need in a programming language, right? So it will allow you to define types, control flow, stuff like expressions, statements, structures, types, just the basic stuff. So you can write a simple program that will declare an array and iterate over the elements and move these elements around to sort it, right? You can do stuff like that with a freestanding implementation. But the standard also defines a hosted implementation, and the hosted implementation will actually support a lot more stuff. So it will support, for example, ways to allocate memory dynamically. It will support perhaps ways to interact with the file system, right? So in C, you can declare a file and use fopen, or you can use IOStream on C++. You declare a bunch of containers in the case of C++. A bunch more, a lot more stuff, and maybe a way to get the time of the day, and maybe threads, maybe. It's depending on the programming language. These so-called standard libraries can be very broad, and in a sense, in order to implement those, you need an underlying operating system, right? You can't really do it. If you try to do it without an operating system, you're going to end up re-implementing a lot of the functionality that the operating system provides, right? And so, these standard libraries are what make it possible for you to get a lot done without caring whether you're running on Linux or on Windows or on macOS or any other operating system, Android. But you can also talk to the operating system if you want from within these programming languages, right? But so if you only support a small part of the non-privileged instruction set architecture, you end up losing access to a lot of this functionality, right? And so if you really want to support completely a programming language, you need the standard libraries, that hosted implementation will provide, and for that you need an operating system. And if you want an operating system, you actually need to implement the privileged instruction set architecture. And the reality is that operating systems and instruction set architectures co-evolved throughout many decades. And they depend, the operating system depends on certain features from the instruction set architecture in which it is running. So I'll give a few examples, right? So virtual memory. It's important that if you have two programs running simultaneously in a computer, you have to be able to separate them and prevent one of them from messing with the other. You need also a way to prevent them from messing up with the memory of the operating system. So you need memory protection. So it's another feature of the instruction set architecture, the privilege. You need in fact different privilege modes, right? It's like the operating system has more power and more rights than your typical program running in a computer. You also need some way to for the operating system to regain control over the processor, right? So you need interrupts in order to do that. And there's a bunch of other features that you need in order to implement the operating system. And none of them are available if you don't support the privileged part of the standard. These are even separate documents, right? And it's much more complicated, much more substantial part of the standard. And so all these other projects that I know of that say they support RISC-V, and this includes RISC-0, includes the Polka VM thing, the new Polka VM thing, they actually support only a small subset of the non-privileged architecture. So you can't boot an operating system directly on them. You can't have these standard libraries of the hosted programming languages available.
Yeah, I guess that's also important because, like, yes, you can kind of build towards, let's say, the unprivileged RISC-V mode and so on, because, like, well, it's just like an embedded device, basically, right? But in my own experience also, it's been really important that I don't need to build the whole world again, like a little bit like with EVM, that I need to implement every single little thing because there's nothing really outside except for, let's say, all the smart contracts. And most of the world is running on kind of like all this software that already builds for RISC-V, so I think that's very important. For those who don't really understand that much, could you talk a little bit about kind of like virtual machines versus emulators and those kind of things, like to explain a little bit like what's that actually about?
Yeah, so people usually talk about VMs when they're running. For example, everybody's familiar with the EVM, right? And most blockchain projects out there have some VM of some kind, right? And these VMs that these projects are talking about are in a sense similar to the old Java virtual machine, the JVM. Lua has a VM of its own. Python has a VM of its own. Like they all have VMs. So these VMs, they were designed as the target for some programming language. So that's what they are. But the word VM, the virtual machine, like the terminology virtual machine, has been used to describe concepts that are very, very distinct. And it's a bit messy. So the only thing they agree on is that a VM is something that can run a program of some kind in some kind of an isolated environment, right? So that's my understanding of the only common thing between these different types of VMs. So I'll give another example of a completely different beast of a VM, right? So you can run a container, a Docker container, and if you're on Linux, let's say you're on Debian, and you want to boot a Ubuntu container to just launch an Ubuntu container. Some people would say that this is running on a container, and other people say that they're just launching a VM, but it's really just a container. But what it's doing is, since you're running the same operating system on the container and outside of the container, and let's say you're using the same architecture as well, they're both x64, right? So you can share even the operating system kernel between these two things, right? So that is in fact what Docker does, right? It will use namespaces and C groups, and it will actually run a program inside a container. The program will think that it's running on a separate computer. You will have access to only a few things, a limited amount of memory. Perhaps you shared a directory with it. Perhaps you didn't, and it's running there, right? So now let's say you're trying to run the same Ubuntu container, but now you're on Windows, right? And you're trying to do that on Windows. So if you try to do that, now obviously you can't share the operating system because they're different operating systems, right? But if the container and if your Windows is also x64 and the Ubuntu that you're booting is also x64, you can actually run it. You can share the processor and the memory, for example, and this is in fact what Docker will do. It will actually use Hyper-V and run what we call a hypervisor. So if your processor supports this hardware extension, you will actually Windows will actually work as a level 2 hypervisor, I would call it, right? There is Windows is a host OS. You will actually spin. Well, now this is actually what we call a VM. You will spin a virtual machine And inside this virtual machine, it will run Windows subsystem for Linux, and it will boot Ubuntu inside it. And it's using the same processor. It's running at bare metal, if you will. But whenever the Ubuntu tries to access certain devices, it will get trapped and will be handled by Windows on the outside, right? Now, let's say you want to boot RISC-V Linux on it doesn't matter, either Windows or your Debian that you had there. Now the architectures are different. So there's no way that you can share even the processor, right? So in order to make this work, you actually have to run a piece of software that will emulate the hardware. And so this is in fact what Docker does. It will actually run QEMU, which is a QEMU, whatever, I don't know how to say that. It will actually run an emulator that emulates the RISC-V processor, the memory, the hardware, whatever hardware you might configure it to support. And your Ubuntu, RISC-V Ubuntu will run inside QEMU. Now, there are a few distinctions between these three types of ways of executing, right? The container directly, when you're sharing the kernel and the processor, or the hypervisor way in which you're just sharing the processor and the memory, but not the kernel. And then the emulator in which you're not sharing anything, right? You're actually separated by the emulator itself. You lose performance as you move along, but you gain isolation, right? So the emulator is the most isolated of all, but also the slower. And so these are completely different concepts, if you will, right? And then there's this fourth concept, which is different as well, which are these VMs created to run programming languages, right? These VMs, you can't really boot an operating system on top of them because unless they are running an emulator inside them, so you have this double emulation issue, right? Anyway, I'm rambling a bit, but this is more or less the distinction. And that's why what we do is what we call an emulator, because that's what we do. It's similar to QEMU in a way, right?
You mentioned earlier that kind of like all the state is machine state is in memory. Like why is this actually important? I know that it has to do with the fact that we might want to, for example, to prove something to the blockchain or like run a CPU cycle or something like that. But could you kind of like explain a little bit about like why is this actually an important property of the Cartesi machine?
The transparency, yeah. So. Do you want me to talk about the bisection as well?
Modularization and then bisection.
Yeah. So the way this works is more one way to run a computation off chain and have it verifiable is that you need to agree on what the computation is about, right? And so in our way of doing things, we define a computation with a hash of the state of the machine. And so this hash of the state of the machine captures completely the entire state of the machine. And in a sense, it forces that the next state, it defines what the next state will be indirectly, right? Because the machine always behaves the same way. If it has the same state, the next state, it's going to be always the same. And then the following state, we already know what it will be, and so on and so forth, right? So it's kind of predefined. The future of a machine, if you know the initial state of the machine, all its future states are already locked in place, right? So what you do is, first you get people to agree on the hash of the initial state of the machine. And you can imagine this machine has a certain flash drive with a file system on it, and it's configured to boot Linux. And here's the kernel. It's also part of the state. It was loaded into memory. And And when it boots, it's going to run your program that is going to look at some other flash drive, perform some computation, and write the result on a final flash drive. It doesn't matter how you set this up, but you have a lot of freedom because it's a full operating system, right? But the thing is that once you agree on the initial state of the machine, then if you're being honest, all future states are already predefined. And so I would take a machine with a certain state, execute it, and then at some point it will tell it will decide, the machine will halt, right? It will say, okay, I'm done. There's nothing else that I can do here. And you'll do the same thing. Your machine will also halt. And if we're being honest, they will halt in the same state. We can compute the hash of the final state, post to the blockchain. And if we're both honest, no disagreement will happen, right? But now we need a way to inspect the contents of the machine that has a certain hash. Right? And so if this was just an MD5 hash or a SHA hash of the entire thing, the only way to do this would be to upload the entire state of the machine to the blockchain, right? And say, see, this is the state that has the hash, but this doesn't fit, right? The state of the machine doesn't fit in the blockchain. So you can have maybe, I don't know, like 128 megabytes of flash drive, maybe another, even more memory. There's no way you can do this in the base layer, right? So instead, we use a Merkle hash of the state. And a Merkle hash has this property, which is really interesting, that if your state takes a certain space, you can produce a proof of the value of any piece of it, and the maximum length of this proof is logarithm in the size of the state, right? And it can easily be verified. So let's say somewhere in the memory of the machine there is a word that tells whether I won or you won, right? And if we agree on the final state, I can then prove to the blockchain that that word says that I won, right? And so you can imagine operations like this, and much more sophisticated than this as well, but it's doable, right? So this is why every part of the state in our machine has to be in that Merkle tree, right? And we could put these things in random places, but then we had to remember where is what, right? But the machine, the machine itself already has an address space, right? It has a 64-bit address space. And so what we do is we make this address space, we reserve small chunks of this address space to represent internal state of the machine. So there will be a region of the state that, so let's say the RISC-V machine has a bunch of registers, for general purpose, has a bunch of floating point registers, has like the floppy drives, the RAM. It has a bunch of other control registers that only people that write operating systems care about. And each of these things, we reflect them in this address space. And then the Merkle, the machine hash is basically a Merkle tree of this entire address space. Right? And so now let's say we disagree. Let's say we disagree on the final hash of this machine. Now we have to fight, right? And there are many algorithms to do this, but they all work with our machine because it has all the properties that these algorithms need. But the easiest to understand is this verification game one, and between two people. And so the idea is we agree on the initial hash, we disagree on the final hash. And so let's say out of the two hashes, the machine that ended first ended at a certain cycle. Let's say started at cycle A and ended at cycle B. So since we disagree, we know that we have to disagree between these two hashes, right? And so one of us will be forced by the blockchain to post what it thinks is the midpoint hash. And the other one will have to tell whether he agrees or disagrees. And so if we agree on the midpoint hash, then we know that we're between the middle and the end. And if we disagree on the middle hash, then we know we disagree between the first, the initial hash, and the middle. And so the disputes continue by bisection, right? And at some point, we reach a state that we agree on the hash, but the next state of the machine we disagree on. And so there is a mirror implementation of the Cartesi machine that can run on layer 1, on the base layer. And this machine receives a log of accesses from the emulator. So the emulator, while it's executing an instruction cycle, it can log all the accesses that is performed. Oh, I'm accessing this word here. Let's say it's the PC, right? It's the program counter. Oh, now I'm going to memory to fetch the instruction at this address here. And now I am going to go to this register and read the value. Now I'm adding 1 to it, and I'm storing, it stores all these accesses. And so the blockchain implementation can actually read these logs. And since the state is Merkleized, these logs come with proofs. Whenever there's a value that is read, it comes with a proof that the value was indeed there from the state hash. And so the blockchain implementation performs exactly the same steps, and reading from the log, it can decide whether the log was acceptable or was in fact dishonest. And so one of us will provide a log, and if the person is being honest, they'll be able to provide a log that advances the state to the state that they claim is the right one. And so that's what a winner would be. And I'm mangled a bit the explanation, but I mean, you guys can read online about how this works. But the important part is that in order to support this type of algorithm, you need a machine that is transparent, that captures its entire state in the hash. And this hash you have to be able to prove that, given a certain state hash, the value of these words are these. And here's how to update the state hash after you've written a word to it, and so on and so forth. You need to have these properties, right? So it's not something that any normal emulator would be able to provide, right?
So that's this kind of like new thing that got introduced kind of recently as well. It's still a little bit in progress, but like this microarchitecture thing, like why is this actually important? Because like you guys used to have like let's say more full with privilege mode and so on, kind of like step on the blockchain and everything. So yeah. What changed your approach besides the fact that it's really difficult?
Yeah. So we had, as we said, the emulator that we are running is like implements a full-blown instruction set architecture from RISC-V, right? The privileged and non-privileged, and a bunch of these extensions. And as I also said, there has to be a mirror implementation in the blockchain that knows how to advance the state of the machine by one cycle. And we started having problems when we were implementing the TLB. TLB, don't need to care about what it is. It's a cache that speeds up translation of addresses between virtual addresses and the physical memory. And it's what makes virtual memory usable in both a hardware processor and an emulator as well. Everybody has to implement the TLB if they support virtual memory. And some of the operations that we had to implement would be very difficult to implement in the blockchain. I'll give an example. Let's say you want to flush the entire TLB, right? So now if you have an implementation like that on the blockchain, you have to iterate over hundreds of thousands of entries if you want to have a big TLB. Our TLB wasn't that big, but it was becoming questionable whether we wanted to execute something like that directly on base layer, right? In case the dispute happened exactly at that time. And so for a while, we ran with the TLB disabled because of that, because we felt that it was dangerous to implement it in the blockchain. And then we decided to implement floating point instructions. And floating point instructions are a problem because the standard is loose in a sense. So there are certain operations that are very well defined, right? So if you add two numbers, it's very well defined what will happen, as long as there is no overflow, as long as there is no underflow. But when you start getting into these corner cases, let's say you divide something by 0, you shouldn't have done that, or let's say you add two numbers that are too big and it overflows, or then you start getting into regions on the standard in which you say, yeah, do whatever you want, basically. Just the representation is not unique, right? So different processors will produce different results in many cases. So it's not reproducible. So you can't really rely on that my floating point hardware in my host computer will be the same as yours. And so even honest people might disagree. So we actually have to implement float, and which means that we would have to implement the same soft float in Solidity. And soft float is a big piece of software and nasty, and the probability that there might be some mismatch between the two implementations, it starts growing, right? And then we decided to implement Hypervisor. Hypervisor is an extension that allows us to actually run containers or VMs inside the Cartesi machine. We can run programs separate from each other and protected against each other. Maybe you want to, your application wants to run untrusted code, right? So you could spin a VM inside and run it safely in a sense. And so, and that is a giant extension. And so implementing that in Solidity would be really, really, really problematic, right? And so, but it's okay, so we need to do something else. And this is what we came up with. We implemented a micro emulator, and this micro emulator actually implements only a tiny part of the RISC-V. And then we wrote our emulator in a way that we can compile the big emulator, the one that implements all the bells and whistles. We can compile it to run in this small emulator. So now our emulator has two modes of running, right? Two modes of operation. We can run the big emulator directly on the host, and between instructions, big instructions, you can stop at any big instruction and the state of the machine will be normal. It will be what it is. Now, the state of the machine now includes the state of this micro emulator. And this micro emulator, it is kept ready to execute the big emulator on its own. But if you're not using it, right, it's as a known state. So it doesn't change because you're moving on the host from big instructions to big instructions. But once you stop at a big instruction, you can then engage the micro emulator and get it to execute the next instruction on its own, moving by RISC-V micro instructions implementing the big emulator. You can stop anywhere there as well. Okay, so now you have this emulator that the state of the big emulator contains the state of the micro emulator inside it as well. It's Merkleized, like it has its own registers, its own memory, and you can run the big emulator on the host, and it doesn't touch the micro emulator. It runs just as before. It's as fast as it is before we introduce micro emulation, right? But if you can stop the big emulator after a big instruction, right? And then you can engage the micro emulator and make it run the code using microcycles, right? You can make it run the code that the big emulator, that implements the big emulator. And you can stop the execution of a big instruction in the middle anywhere. So remember that example. If that one big instruction, let's say, triggers TLB flush, in the code of the big emulator, there will be a for loop that goes over all entries of the TLB and starts setting them to 0 or whatever is the default value there, right? Now the microemulator can stop that for loop anywhere in the middle of the execution, right? So the cool thing is that this microemulator produces exactly the same state after it's done executing the big emulator. And after it gets reset to its initial state, the microemulator gets reset to initial state. What you have is a machine, exactly the same machine as if you had executed the big emulator directly on the host for that cycle, right? So now we can go back to that bisection example that we were talking about, and I agree on the initial state of the machine, which is a machine ready to execute the big instruction, and we disagree on the state, on the final state, with the state that the machine was after executing a certain big instruction. And so now we can start bisecting. At some point, we'll reach a situation in which we agree before a certain big instruction was executed, but we disagree after a certain big instruction was executed. And in the past, we would have to go to the blockchain and execute the entire big instruction. But now we switch to the small emulator, to the microemulator, and we start bisecting within this big instruction. And until we reach a point in which we agree on the state of the machine, entire machine, at a certain micro instruction.
So I heard that one of the things about the microarchitecture is that it makes it, let's say, much more simpler to implement, like you said. Like how does that affect kind of like, let's say, security or smart contract version of the things?
Yeah, so now we wrote the microemulator in a way that it's C++, right? But it was written in a way that almost looks like Solidity. So you actually can generate the corresponding Solidity with just a search replace, and the code looks almost the same. So it's very easy to audit and make sure that the code of the microemulator as implemented in the emulator is the same as the code of the microemulator as implemented to run on the blockchain. So that is great for security, because earlier this big emulator was implemented in the blockchain, and that had thousands of lines of code, right? It was really big, but now it's really small, and you can just see it running. Now the trade-off is that as long as the compiler that we're using to compile the big emulator to run on the host behaves in the same way as the compiler that we use to compile the big emulator to run in the micro emulator, then we're good, right? We need to make sure that when we write the big emulator, the set of steps that it will perform on the host or in the microemulator are the same, at least between micro instructions, right? And so that is the only we moved it to something that is automatic in a way, right? So if there is a compiler bug, like a serious compiler bug, then we're in trouble, right? But it's less common for you to have a compiler bug than you have a human bug. And so we need some, it would be nice in the future to have some verified code generation for both cases. And there are tools that do that. We're investigating. But this frees up our creativity in implementing the emulator to support much more complicated operations, right? And for example, in the future, as I said, we wanted to implement floating point instructions. Now we have. We wanted to implement the hypervisor. Now we have. Now we might want to implement some optimizations that would be really difficult to do in the blockchain, like trace compilation, even jitting, and we would be able to do that now that we are free.
So I think that kind of leads to the next question, which is about this, that now the emulator kind of supports this RV64 GC, and why is it important?
Yeah, so RISC-V, as I said earlier, RISC-V was designed to allow different implementations of the standard, right? The standard is broken down into a bunch of extensions. So you have you might have the base instruction set support only 32-bit instructions, and then you have an extension that adds multiplication instructions there, and not even part of the base instruction set. And then you have another set of extension that supports atomic operations, and another instruction set that extension that supports 64 bits, and then another extension that supports floating point in single precision or in double precision, or another extension that supports compressed instructions, which is a more efficient way of encoding the instructions. And each person each implementation can pick which extensions they want to support, right? A hypervisor, so on and so forth. Vector instructions and cryptographic extensions. But the reality is that there's a set of instructions, extensions that have gained popularity to an extent that this is what most people understand to be RISC-V. And so this is basically a 64 machine with multiplication, atomics, floating point instructions, both single and double precision, and compressed instructions. And that's called, for short, RV64G, C. Maybe some people add the C later, or some people don't. But the cool thing is that because we support that, and because this is what has been accepted by the community as what RISC-V means, there are now distributions out there, Linux distributions out there with precompiled binaries that work directly on our emulator, right? So now you can just use a Docker file that starts from Debian for platform RISC-V 64, and apt-get install a bunch of stuff, and then transform that into a root file system that you can boot inside the Cartesi machine, right? And so this is a big milestone because earlier on, the way you would develop for the Cartesi machine was more of a embedded device experience that is not as widespread as this new way of doing it, of just getting a standard installation and run. So there's another distinction here, is that earlier on we were using a lot of cross compilation, and now you don't necessarily need to use cross compilation. You can start using these so-called self-hosted operating systems like Ubuntu, or earlier on we were using build root, right, which is something for embedded devices, and now we can start using normal self-hosted distributions.
I think I'll just jump to this one. So with the Cartesi machine, like would you say it's complete at this point, or something like that?
It's complete. It depends on how we define complete, right? It's complete in the sense that it's perfectly usable for most applications. Now it's almost feature complete from the point of view of the inside of the Cartesi machine, but from the point of view of the outside, obviously want to make it faster, right? As the faster we can get it, the happier people get. We will also try to improve the ecosystem, right? So we want to make it easier for developers that had never done embedded development to quickly start and getting their programs running, right? And we want to, we're working on a better version of this verification game. And this better version of the verification game is putting certain demands on the emulator that didn't exist before. So when we designed the emulator for the old style verification game, all you needed was the machine had to be fast until you asked for it to compute the Merkle hash of its state, right? And this was something that would happen very seldom, like it's very rarely. But now we might want to produce a new state hash after every micro-instruction cycle. And so this requires us to do things in a different way, and we're going to work on that as well. There is, for instance, this new demand that the Cartesi machine work on multiple different operating systems. So people want to use it on Windows, people want to use it on Android, people want to use it, actually compile it to WebAssembly and run it inside a browser. People want to do all sorts of things that were not foreseen. And we already improved a lot support for other operating systems, but we still have this dependency on the fork system call that we are considering dropping. So we're going to implement our own alternative that will allow us to do something equivalent to a fork on Windows, for example, or even on WebAssembly or wherever. So there's also this usability thing for prototyping that we want to support, virtual I/O. We already have a PR that adds support for virtual I/O. For those who don't know, virtual I/O is this way of connecting the inside of the Cartesi machine to the outside. Obviously, you can't do this when you're running for real in a way that is reproducible and self-contained, right? But when you're prototyping, this is really useful. So for example, we have added a way for you to share a directory on your host to the software running inside the Cartesi machine. We have added a way to support network connections, so you can apt-get install stuff from within the Cartesi machine, or you can SSH into it, or it also improved terminal support. All of these things violate self-containment. But when you're prototyping your application, this is really convenient. And so we're probably going to merge this, either the next version or the one thereafter. Did you have something else in mind that...
No, I think that's quite good. So I would like to say thank you for taking this time to kind of like go through all these very complicated topics. I think we have a lot more, let's say, topics maybe also to cover in the future. It was very, very interesting to kind of like hear some stories that I didn't hear about before, some details as well. So thank you very much.
Yeah, thank you.